We started the lecture, but let's restart because it is already some days ago, so probably you have forgotten. So this lecture is about resizing images, and it will appear a concept that is very important. So more important than the resizing itself is the interpolation concept. So let's see what it is. So let's say that you have an original image like this one, and you want to make it smaller or bigger. And if you want to make it smaller, normally there is no problem, and almost any interpolation will do a decent job, more or less. But if you want to make it bigger, some of them seem to be better than the others. So this is nearest neighbor interpolation, linear interpolation, cubic interpolation. And you can see the quality, the differences in quality. And so we will see the details of what each one of these interpolations have. And let's start with the resizing itself. So in the resizing, there are two operators that are very important. One is upsampling and downsampling. And downsampling actually has two components. So the downsampling normally is a decimation followed by a filter. You know this, sorry, a filter followed by a decimation. Decimation, you have all these concepts, you have them. Have you heard of those from the signal course, the standard signal course? No? Okay, so let's introduce those two or those three operators. Let me go here. Okay, already prepared a bit. Okay, so let's say that we have a signal like this one. And this is n, this is x of n. And we can implement two operators. One of them would be this one. So let's write the two, and then we'll make a draw. Okay, so let's construct I of n, that is x of 2n. The other one is y of n, that is x of n prime. Okay, so let's start with the second one, which is easier. So the second one would be, okay, so let's say, let's see a few of these values. Okay, so y, well, let's start with the first one. Okay, the first one is easier. So y of 0 is x of 0. Then y of 1 is x of 2. Y of 2 is x of 4. Y of minus 1 is x of minus 2. So we can draw on the original system. We can draw which ones are the ones that goes with the y. So it will be this one, another one, this one. Okay, so those are the ones that go with this one. This one is called decimation. So let's see. So this operator is a decimation by a factor n, by factor 2 in this case. And in the y, in the decimated signal, so let's write the indexes in the original signal. This is index 0, 1, 2, 3, 4. But in the decimated one, this is 0, 1, 2. So there is a compression of the time axis, right? So it seems that the red signal is faster than the original signal. Okay, so yeah, if you think in terms of sampling rate, so the sampling rate of the new signal is twice the sampling rate of the original. So let's call it, this is the sampling rate of X, this is the sampling rate of Y. Okay, so what about the other one? So the other one, this is the upsampling. This is the upsampling. And actually, this is a kind of loose way of writing this operator. So it would be better to say this is X of n hat if n is a multiple of 2, and 0 if n is not a multiple of 2. And then we can write a few of those samples. So we would have y of 0 is equal to x of 0. So the origin stays the same. But then y of 1 is not a multiple of 2, so it is 0. And then y of 2, this is x of 1, and y of 3 is 0. And y of 4 is x of 2. And on the other side, we would have y of minus 1 is 0, y of minus 2 is x of minus 1, and so on. Okay, so let's draw them again here. So we will have this sample, then 0, then this sample, then 0, then this sample, then 0. The same on the other side. And in the blue axis now, this is the index number 0, this is index number 1, 2, 3, 4, and so on. So now, the blue axis, the blue signal, is slower than the original. Okay? And we have filled with zeros. So these are the two decimation and upsampling operators, but typically they are not used alone. So this operator is represented. This operator is represented by this. So this is an upsampling by a factor n. This one is represented like this. This is a downsampling by a decimation by a factor n. And they are used in the following way. Okay, so let's say that we have our input signal X. On the upper branch, we will do a downsampling. So if you do a downsampling, what is the problem? Just in the same way as we have written the sampling, the new sampling rate there. Let's write it for the blue one, just to be complete. So it is 1/2 of the 1 of X. Okay, so let's do a downsampling. So if we have a downsampling, what is the problem that we might have? Yeah, you will lose information for sure. But if you lose information, then what happens in Fourier space? You have aliasing. So, what can we do before doing the downsampling? Apply a filter. Okay, so we apply a filter whose impulse response is whose impulse response is a sensible. If we are doing the downsampling by a factor of n, what is a sensible cutoff frequency? pi over n. So this has to be pi over n. And this is 1, this is omega, and this is the filter. And then we can do the downsampling. You may not remind these things, but they are familiar to you, right? Okay, so what about the upsampling? So with the upsampling, are we losing information? We are not losing information. So we don't have to apply an upsampling filter, an anti-aliasing filter. But we have a different problem. We don't have aliasing, but we have some unpleasant zeros there. So our signal, we know that it is not 0, whatever 0, whatever 0, whatever 0. So all these zeros, they are here because of the operator. But we want to feel somehow, we would like to be this blue point to be somewhere here, somewhere in between, so that we have a smoother signal. So how can you do that? Yeah, that could be a possibility. So you join this by a line, and then you put the sample in between the line. Okay, and actually this is called linear interpolation. Linear interpolation. And okay, that is a possibility. So what you want is to apply some kind of filter, and that is one. And again, it's pi over n. This is omega. Okay, so actually, let's we have y, that is the upsample signal, and if we are filtering it, we are convolving it with the impulse response of your filter. Okay, so if you use this filter, what is the impulse response of that? What is h of n when the filter is this one? It's a sinc. So you are convolving with the sinc. And for the bilinear interpolation, the h of n is a triangle. It's a triangle that has probably this one. So this is h of n. Probably not this one. Sorry. Because otherwise the samples are could be 0. So it is this triangle. So we are convolving with that. Okay. So this is bilinear interpolation. Okay, so this is our general structure. So we have two operators. This is the decimation, this is the upsampling, and then we put filters, one to avoid aliasing, another one to fill the holes in the signal. Okay, so let's see all this with images. So, yeah, and we have already discovered a more general setup in which we convolve the input of the upsample image. We convolve it with something else. We convolve it with something to produce our output. And what we will control is what is this something. Okay, so we have already seen two possibilities. We have the C, we have the triangle, and we will see another possibility, another one possibility. Okay, so yeah, let's see this with images. So let's say that we want to, and in this setup, we could compare with, let me use a different color. This one. We could compare with this. So for instance, if we are downsampling by a factor of 2, if we are convolving with a factor of 2, we could convolve with that. And this one will be called nearest neighbor. Okay, so let's see. Okay, so let's say that we want to enlarge an image. So we have this image and we want to produce an enlarged version of it. So we could start by creating an empty canvas that we call our image. And then we fill in every fourth pixel in every fourth row with the original images. So here you recognize the upsampling operator. So you have a sample 000, another sample 000, another sample 000. That is the upsampling. So to go from here to there, we have written it with words, but what we have here is the upsampling operator. Okay, so we have the upsampling, and now we have to fill in the holes. And to fill the holes, we convolve with a step function. Okay, the last one that I wrote in the whiteboard. So now this is a zoom of the region of the image. So we have our samples and then the zeros in between. And now you convolve with these step functions. And convolving with that step function is simply copying the sample in the corner of these squares, copying it 4 times in all directions. We have this step function. Very bad in flowing that. Okay, so in images, all this theory I have explained in one dimension that you are more familiar with it. But in an image, we would be convolving with something that is 1, 1, 1, 1 everywhere. And then outside, so the origin is here. And then outside, what we have are zeros. So we have zeros everywhere. And they go from minus infinity to infinity. So we are convolving the upsample image with this curve. Okay. And that what it does is take this pixel here in the corners and replicate it for 16 times. Okay, so this is this nearest neighbor interpolation. And then we can see the decimated image. So this is making the image larger. So we go from small to large. So we need an upsample operator. Here we need a downsample operator. So we start seeing at the decimation. So the decimation without the filter. So what we have to do is to take 1 every 4 or every n pixels. So here is a zoom in. So if this is a zoom of the original image, now you are taking these samples in red. So you recognize again the decimation operator. Okay. Yeah, so those are the samples that you will keep, and then you gather them in this smaller image. Okay, good. Then we have seen this nearest neighbor interpolation applied to integer factors. So we can upsample by a factor n, downsample by a factor n, but we can combine the two operators in a single operator that has a fractional scaling factor. So let's say that we want to make an upsample, a rescaling of the image by a factor, by a fractional factor, p divided by q. So let's say, for instance, that our scaling is 3/7. So 3/7 is smaller than 1. So what we will do is a downsampling. Okay, so what we will do is, okay, this is assuming of the original image. So we divide the original image in blocks of 7 by 7. And then you take, inside each one of the blocks, you take a sub-block of size 3 times 3 that is equally separated. So we will keep these samples, and then we collect the samples and put them together into a single image. Okay. So now we are not constrained to have integer factors, scaling factors. So we can have any fractional there. Yeah, this is just a detail of the original image. So we have gone from the original to something that is smaller, and then if you make a zoom, this is what you get. And here we have not applied any protection against aliasing, so you can expect that these operators they have aliasing. Okay, let's do the opposite. So let's make the original image bigger, but now by a fractional factor again. So let's say that now it is 7/3. Okay, so what we will do is kind of similar. So we will take, here it is better explained. So we will take, in the output of in the output image, we will take blocks of size 7 times 7. So the blocks 7 times 7s before they were taken in the input image, not in the output image. And then we will take in the output a subblock of size 3 times 3, and this subblock of size 3 times 3 is coming from a block of size 3 times 3 in the input. Okay, so unfortunately, they don't have a better representation of that. Is it clear how it is done? Okay, so each one of these blocks of 3 times 3, they are coming from the input. Okay. So in the input, we are not losing any information, and we are filling it in the output image. And then you have to fill in the holes, and to fill in the holes, you go for this nearest neighbor interpolation. So you copy the pixel that is closer to you from where you have information, and unfortunately you see that the holes, they don't have the same size. So here the hole is of size 1, so we have a missing number, but here we have 2 missing numbers. So it is not a convolution anymore. So a convolution has a fixed kernel. So we don't have a fixed kernel, but the kernel has to vary in size. Okay, and we will see better ways of doing these upsampling and downsampling. Okay, but this is a problem of this technique. Okay, I like better this definition of the nearest neighbor resampling. So the other ones are pretty visual. We understand how they work, but again, you're engineers. You should understand this in terms of mathematics. Okay, so this is a more mathematical description of this process. It's here. So let's. Okay, so here what we have is, let's say that we have an input image of this size, R columns, R rows, C columns, and we want to produce an image of this other size, of this R prime and C prime. So we will have two scaling factors. One for the rows, one for the columns. And we will concentrate on this part. The other ones so the other branch is just a very technical thing. There is a pixel that you are missing, or there is a sample that you are missing if you go in one direction or the other. So one direction or the other means, so this direction is this direction here. R is larger than R prime, so you're going from large to small. And this other direction, you start with small and you're going to large. Okay, so yeah, but let's forget about this distinction and we will treat both in the same way. So the important thing is the scaling or the ratio between what is the original size, what is the final size. Okay, so now we have these scaling factors. We have them here, so we have the two scaling factors. And in all these approaches, or in all these operators, that this is a geometrical operation. Okay, a geometrical operation in the sense that we are making the image smaller or bigger. We will see more geometrical operations later in the course when we are rotating the images or warping the space or whatever. So in whichever operation in which the space is expand or it contracts, then those are geometrical operations. So in all those geometrical operations, you always start from the output. So this is a coordinate in the final image. So that is why it has this subscript F. And then you have to look from the input image where it is in the input. So this coordinate in the output has to be taken from this coordinate in the input. Okay, so we always go. So let's say that we are making it smaller. So we have a big image, we have a small one. We always have to say this coordinate is coming from here. You always go in this direction. Okay, so you need a transformation that takes coordinates in the output. So this coordinate, let's put some colors. So let's say this is the output, and this is the input. So this coordinate here, R prime, C prime, is in the output space. This fractional coordinate, sorry, F is for fractional, not for final. And this coordinate here is in the input space. Okay. So this coordinate in blue is coming from the output. Then we have some transformation in green, and then we produce a fractional coordinate in the input space. Actually, if you look at what we were doing here, we were doing that exactly. So we avoided the fractional by this distinction of multiple of 2, not multiple of 2. But otherwise, we would have here a fractional coordinate. So if I leave just this transformation, let's write it in blue again. Sorry. Here you have the fractional coordinates. So y of 1 is x at 1/2. That I don't have it. Okay, but I have here my fractional coordinates. So in the color code that we had before, this is my coordinate in my output space. This is my output space. And this is my fractional coordinate. This one is my fractional coordinate in my input space. Okay, so let's go back to here. So this is our transformation. And in general, you can think of this, and this is what we will do in other lectures. This is a function of r prime, c prime. And then this function can be whatever. So what we are seeing here is just a particular shape of this fraction. So a particular shape of this function that is we will scale the input coordinates by something. Okay, so now how do you do the scaling? So you loop over all. Do it in the same color. So you loop over all the coordinates in the output, then calculate the fractional. The fractional somehow it is here. So you calculate here the fractional. So you calculate RFCF. And once you have RFCF, you have to. This is a fractional coordinate that you don't have the value there. So you have to figure out what value to put. And this will be the output. So what you will do, actually, this is in the input space. So in the input space, it's right. So you will round the fractional coordinates to some integer coordinates. And for that integer coordinate, I have the value. And then my output, this is my input, this is my output. And my output at r prime c prime will be the input at r bar c bar. Okay, so this is a very easy transformation. And all these, I find it more natural to explain it in this way. So to express it in terms of coordinates, functions, or what are the operations that you do with the functions. But visually, if you think of this process we have described in the slides, this is what we have done. So this process of taking blocks of size, it was very nicely shown here. So taking blocks of size 7 × 7 and the coordinates in yellow and so on. It is exactly the same that we have described in that algorithm. Okay. Any questions? Okay, then so let's think a bit more about these fractional coordinates. So let's say that we have this input image, that we have a sampling rate that it is 1, so the distance between one coordinate and one pixel and the next is 1 pixel. And let's do a resizing. So let's do a downsampling or a downscale. So this downscale will take, this is the 0, 0 coordinate. So the 0, 0 states as we had in the 1D signal. You may remember y of 0 is x of 0. So the first pixel stays. And then the next one, because we are going from large to small, we will have a sampling rate that is a little bit bigger than the original sampling rate. So it will not be located exactly at the distance 1, but at a little bit bigger distance. And the same in the other direction. So those are the points that I would like to sample. But those are fractional coordinates, and I don't have them. Okay? So that is why we have this nearest neighbor interpolation for the moment that help us to tell us what is the value there. This is in the opposite direction. So let's say that we want to make our image bigger. So now the sampling rate is smaller. And then we will have closer samples. So we will have this one, and the next one is not at the distance 1, but the smallest distance. The smaller distance. Okay, so yeah, and this is what I told you before. If you use this factor, just the ratio between the two sizes, that is one sample that goes out from the output image, and then you can fix it by redefining your scaling and saying R-1. But this is a very technical detail for just one pixel. So the important part, even in here, is the ratio between R and R prime. And all this reasoning, all these slides now, they are thinking about where the pixels, the output pixels are coming in from the input and so on. But we have made that reasoning in one dimension, so we understand it already. So we don't have to go through this hassle. Okay, so let's keep all these slides. Any questions so far? No? Okay, so let's go again to so we had this upsample signal that we had a point, then a 0, then another sample, then 0, another sample, 0, and the same on the other side. So this is y of n, this is n. And what is nearest neighbor interpolation? Let's make nearest neighbor in V. Nearest neighbor interpolation is simply replicating, for the 0, is replicating the 1 on the left because of this rounding. Because of the rounding, we are replicating the 1 on the left. But we had a better solution. We had, for instance, we could join noun samples with lines, and then substitute by evaluate that line at the location we are interested in, and then that is our sample. And we have already learned that this way of joining with lines is equivalent to convolving with the triangle. But yeah, let's forget about the convolution. These other possibilities called linear interpolation. This is nearest neighbor interpolation. Neighbor interpolation. And this one is called linear interpolation. Interpolation means you have to invent the value. So you don't have the values here in the middle. So you have to figure out what that value is. And you have to figure out that value from the information you have around. And that is called interpolation. Okay, so here is the result with nearest neighbor interpolation. This is the result with bilinear interpolation. And we can see here, this is the result with nearest neighbor, where we have a sample and we simply replicate it. And this is the result with bilinear interpolation, where we see that there is a smooth transition between, for all these pixels here, there is a smooth transition from the four corners to the values in between. See that? You see? From the four corners, we have a smooth transition from these gray values to any value in between. Okay, so let's see how to do that. Okay, so let's say how it was done in one dimension. So in one dimension, I wanted to figure out the value here in the middle. So what I took was the two samples that I knew, one from the left, one from the right, join those two samples with a line, and then evaluate that line at the location I'm interested in. Okay, so what is equivalent in two dimensions? Two dimensions, let's say that I'm interested in, those are the holes that I have. So in two dimensions, I don't have just one sample on the left and one on the right, but I also have one at the top and another one at the bottom. So I can take the four samples around. So let us see again here. So to evaluate any one of these 4 or 15 samples, I have 15 holes here, I have 15 zeros. So to evaluate any one of these 15 zeros, I will take these 4 samples around. Okay, so this is the equivalent of one on the left, one on the right. Which 4 samples? These ones. Okay, so I will take the ones with the red ones. And then instead of fitting a line, the equivalent of a line in one dimension is a plane in two dimensions. So we will fit a plane, we will fit this plane, and evaluate that plane in the locations you are interested in. Okay, so let's make a break. Okay, so let's think of this statement that the equivalent of fitting a line in one dimension is fitting a plane in two dimensions. Okay, so let's think why that is the case. Okay, so let's say that we have x, y, and we have a line. So you know the equation of line is something of this form, ax plus b. Okay. But I can rearrange this, and I can say, okay, this is ax minus y equal b, equal minus b, right? Do you agree? So this is the inner product between a vector that is a1 and then xy, and this is equal to some constant. Okay, so in general, the equation of a line is the inner product between a vector u, the coordinates x, equal a constant. Do you agree that this is the general equation of a line? Okay, so let's say we are we are fitting a plane. Okay, so we have x, y, z, and we have a plane here. And you know the equation of a plane is something like this. Do you agree? This is the general equation of a plane. But I can rearrange it again the same way as I did before and write it in this way. And again, I have the same structure as we have. So we have a vector that is a, b, minus 1. And then we have the coordinates, x, y, z. And then this is equal to a constant. So it has the same structure. So this structure here is actually the equation of any, and there is something very interesting, that is this u vector is perpendicular to the plane of the line we are defining. So this equation here is called the equation of an hyperplane. So an hyperplane is a set of dimension. So let's say that x is a n-dimensional vector. So this equation defines a set of points that lie in a world that is n minus 1 dimensional. Okay, so the points that fulfill this equation lives in a surface or in a manifold is the right word. So live in a manifold whose dimension is n minus 1. So this one is n minus 1. And we can see it here. So here we have two-dimensional coordinates, x. The vector x is two-dimensional. And the points in the line live in a one-dimensional world. Here we have points that are three-dimensional, and the points in a plane live in a two-dimensional world. So in general, if we are in dimension n, this equation here defines an hyperplane that is an n minus 1 dimensional world. Okay, so fitting a line in one dimension and fitting a plane in two dimensions is the same. So they both are hyperplanes in their own dimensions. Okay, so we are fitting a plane. So there is only one plane that goes through those 4 points. And then we can evaluate that plane wherever we want. So we evaluate in those 4 places, or in the case of the 4 times 4. In the case of the upsampling by a factor 4. So we feed the plane through these 4 points, and then we evaluate this plane in all these locations, the 15 locations we are at. And here we have some results. Okay, so let's enlarge this image by a factor 4. So this is a zoom of that region, and then further zoom. So this is a. So for the bilinear interpolation, we start with the upsampling. So we apply the upsampling operator. So now we have the zeros in between. And this is the result of the nearest neighbor interpolation. So we take the pixel that is closest to us in the top left direction. So this is the rounding, and we copy it. Okay, so all these pixels will have the same value. But now we can apply the bilinear interpolation. So for the bilinear interpolation, we have these points, for the ones with colors, and the ones in red are the zeros. So now we fit that plane, evaluate the plane, and this is what we get. And you can compare to the nearest neighbor interpolation. So this one is smoother. So the nearest neighbor interpolation creates artificial edges between regions of the image. So these borders here, they don't exist in the original image. It is simply an artifact of the nearest neighbor interpolation. But with the bilinear interpolation, we have a smooth transition.
Yeah. And in this table, you said that we get the pixel from the top left.
Yeah.
So I have all
Top left. So you copy all these pixels. So all these pixels here, they take the value from here, and all these pixels here from there. Okay, and the same here. All these pixels, they take it from this point. Okay, so yeah, these are different versions of the same. Yeah. Okay, so and when you look at the result, not so soon, but you notice the difference in quality. So this is by nearest neighbor interpolation. This is bilinear interpolation. It is called bilinear because we are fitting a plane. And in the 2 dimensions, so here is our plane. So in this direction we have a line, in this direction we have another line. It is a bilinear interpolation. Okay, then yeah, and so let's compare this image that we had of the cactus and that we made the reduction by a factor of 3/7. This was the approach of the nearest neighbor interpolation. So we were taking our samples from the yellow points. Now with the bilinear interpolation, we are taking the samples from the red points. So those are the fractional coordinates that we want to evaluate. These ones here in red are the ones that we want to evaluate with the plane fitting. And that is another advantage of this bilinear interpolation. I mentioned before the yellow ones cannot be expressed as a convolution because the distance between the holes that I need to fill in some places are of size 1, but in some other places are of size 2. And I don't have a single kernel that allows me to interpolate those 2 or 1 zeros. But now the separation between the red points is totally homogeneous. So you can see that the distance in all directions of both in both directions between any 2 red points is always the same. So I don't have that problem anymore. Okay, so let's say that we want to interpolate at these red points. Okay, so let's see how to do that. Now we have a zoom. So yeah, and let's look at these 7x7 block in the input. So that will be a point that stays in the same location. So this one doesn't need to be interpolated. This plays the role of the 0, 0 coordinate. So the 0, after the scaling, it doesn't move because it goes to 0 again. But what about the rest? The rest I have to interpolate. Okay, so let's yeah, this one I don't have to interpolate. This is fine. But this one I have to interpolate because I have the values, I have the samples at the middle of my pixels, but I want to know the value here in blue square, and I don't have it. So that is a trick that we have discussed of fitting a plane with these 4 corners and then evaluating that plane at that location. And the same here. So we have other 4 corners, and we want to evaluate at that point. And yeah, those are the interpolated. These ones here are the interpolated values. So you see that somehow they lie somewhere in between the 4 corners. So this pixel here, it has a color that is more or less in between the 4 values around. And this more or less in between is defined by the plane. And we have discussed fitting a plane, but if this is a color image, we have 3 values. They are giving values. So we are fitting 3 planes. One for the R, one for the G, one for the V. Okay. Yeah, so this is the result through bilinear interpolation. Okay, so let's look at the bilinear interpolation in a more quantitative way. So I have said we fit a plane, but I have not defined what is the equation of that plane. So let's define the equation of that plane now. So we have 4 values. So let's say that I want the coordinate here in this location, this R fractional, C fractional. And we have the 4 corners around. And the 4 corners around will be called RC. Then this is RC plus 1. This is R plus 1C. And this is R plus 1C plus 1. And we will define the distance between what is this fraction. So let's say that we want to interpolate at the pixel 7.3, comma, so comma for separating rows and columns. So 7.3 and 1.5. So this will be the pixel 7.1, okay, because we have 7.3, 1.5, so this is 7.1. So what is the distance between my 7.1 and my 7.3, 1.5? So it is this in columns, it is 0.5, and in rows, it is 0.3. Okay, so this is the delta C, this is the delta R, this is the part of the fraction. Okay, so here is the integer part, this is the fractional part. Okay, so we want to scale. So now for the scaling, let's do the same thing I did before. In the this new. Can I copy that? No. Okay, so let's how do I close? Doesn't matter. So new. Okay. So we take this one. We copy. Okay, here we are. Okay, so we have the scaling factors. The scaling factors are the same. The transformations from I don't remember the colors I used before, but the transformations from the output, this is out, the input, it is the same, so the same as we had before. And this is giving us this point. But now we have to make it integer. And to make it integer, we separate, or we take that fractional coordinate and we separate it into integer and fractional part. So this is the integer part. So we round down. This is giving us this point. But then we compute the fractional parts. And these fractional parts are these two. Okay, so just to put numbers, this is the 7.3, 1.5 as I mentioned before. Sorry. This is in blue. This coordinate is in blue. And then, this is 7.3, 1.5. And this one is 7.1. And then we have the 0.3 here, 0.3 here, 0.5 there. So this is 0.5, this is 0.3. These ones here, this is 7. Okay, and we have the 4 coordinates. So let's make this one is the red one, and then let's use other color. So this is r plus 1. R plus 1 is this one. And then we have and I have run out of color, so let's make a spread. So we have those 4 colors. And these ones here are the weights. Do you remember the equation of a plane? So we said the equation of a plane is something like this. So it is ux, uy, uz times x, y, z equals constant. Do you remember? So we have some weights multiplied by the coordinates we have, by the values we have. So those are the weights. These ones here are the weights. Here we have 3 weights, here we have 4, but because the 4th one goes to the k. So one of them acts like something that goes to the k. But okay. So we understand now how this is constructed. So let's look at the different weights. Let's see that if they make sense or not. Okay, so let's replicate the figure again. I will make it. So let's say that we have this picture. This is where I want to interpolate. So I want to interpolate maybe. I want to interpolate it in that location. So delta C is small. This is delta R. So delta R is small, and delta C is also small. Okay, so the value here should be close to which value? So my value at R fractional C fractional should be more or less which value? This one here, right? Should be very similar to that because it is very close to that location. Okay, so let's see if that is the case. So we go into the plane equation. So we go to the plane equation. And if delta C, delta R is small, then this term is high because it is 1 minus delta R, 1 minus delta C. So I have a high number here, a high number there. What about this one? Delta is small, so this product is almost 0. Delta C is small, so this product is almost 0. And here both are small, so delta R, delta C. So this other term is also close to 0. So the most dominant term is this one that has high values. And it is close at R prime, C prime, it is close to R I of RC. You see? I mean, if you make the same reasoning for any other location, you see that the pixel is taking the weight, the large weight from the closest pixel. Okay, so if you do the same reasoning at now with a different point, this one here. So now delta R, delta C, they are large. So delta R is large, delta C is large. Okay, so let's come back to the equation. So delta R, delta C are large, so 1 minus delta R is small, 1 minus delta C is small. So this is almost 0, this is almost 0, this is almost 0, and this is the one that remains. Okay, so it seems that it is going in the right direction. So this is the equation of a plane. It has the right weights, and we see that the results are really good. So or at least much better than the nearest neighbor interpolation. And this is the same I have explained now here in the slides. Okay, and this is the same process we have described, but now it is summarized in this algorithm. So if you want to go from a size to another size, then you define your scaling factors, and then you define a way to go from coordinating the input to coordinating the output. Sorry, from coordinating the output to coordinating the input, and then you take the left top corner. So this is the integer part of that coordinate. This is the fractional part of that coordinate, and then you apply these weights. So it is a summary of what we have seen. Yeah, and here you have, for instance, this is the original image, and this is the result if you make a reduction. This is the result if you make an enlargement. Here is again the same process, but now what if I have color images? So if I have color images, then those pixel values, they are vectors, they are not scalars. But it doesn't matter, the same formula applies. Actually, here, you may not have noticed, but we have used bold letters. So bold letters means this is a vector. So we have the RGB components inside. And actually we are not fitting a plane, but 3 planes at the same time. One for the R, one for the D, another one for the B. Okay, so, but the formula applies. So let's say that we have this, we want to interpolate this pixel here. These are the values at the corners. And what we have to do is, okay, so let's take the left top corner, that is, I think this is an equal, okay? There is some mistake here. This is an equal. And so we take the top left corner, that is this one. So this goes here. This one is this one, and so on. And these are the weights. So let's say, okay, so I'm close to this one. So it is 1 minus delta R, 1 minus delta C. So 1 minus delta R. In both directions, it is 2 feet, the fraction. So 1 minus 2 over 5 is 3 over 5. Okay, so we have 3 over 5 squared, and then this one is farther. This one is farther, so they have a little bit smaller weight. This one is much farther, so it has the smallest weight. And then this plus 0.5 and then rounding down is a 3. So this is a 3, computational 3. So we have already discussed of 3 ways of rounding. So this is rounding to the closest integer. This is rounding down, and this is rounding up. We have to discuss about these 3, right? Okay, so this is called round. This is called float. And this is called zero. Okay, when you work with floating points, so let's say that I have a number like 7.3210 whatever. This is a float. We have float x equal that. Making the round of x, of x as a floating number, it will take some time in the computer. So there is a trick. This is equal to taking the integer part of x plus 0.4. And this is much faster in the computer. So adding 0.5 is very fast. And taking the integer part of that is also fast. Okay. So this is this trick here. This is very much used very often in many computer programs. Okay, so we take, we make the calculation in floating numbers, then we add 0.5 and we round down. Okay, so yeah, linear interpolation. Any question? No? Okay, so we have said I want to interpolate at this point, at this location, and then I take the 4 pixels around and I fit the plane. Why constraining to just 4 pixels around? Why not taking a bigger area? So we could take, instead of 4 pixels around, we could take 16 pixels around. And we know better how the function looks like in that area. So if you think of an image as a function, so let's do it in 1D first. And then we go to more dimensions. So let's say that I have x of n. I have my samples here. But my samples are coming from a function. My function, let's say, is this one. That is smooth, but whatever. And by doing the bilinear interpolation, what I'm doing is approximating this function by segments, by straight segments. But when you look at, for instance, here, your line segment is not totally equal to the original function. There is a difference. So why couldn't the line take more? Because it is just taking 2 points. And from 2 points, I have only the possibility to fit a polynomial. If you have 2 points, you can fit a polynomial of degree 1. Now let's say that we are allowed to take this point, this point, this point, this point. So now with 4 points, what is the degree of the polynomial we can fit? Degree 3. So now I can let's do it. With 4 points, I can fit. You can count the number of constraints here. So we have 1, 2, 3, 4. Number of coefficients we have. We have 4 coefficients. Here we have 2 coefficients. So So with 2 points, I can fit 2 coefficients. With 4 points, I can fit 4 coefficients. Let's look at the segment approximation. The segment approximation is continuous. Is it or not? So the red approximation is continuous. It is. I start here, and then at this point I change my direction, but there is no discontinuity there. And then I go here, and then I go here. There is no discontinuity. What about the derivative? The derivative is continuous. The derivative is not continuous because this derivative here is different from this derivative there. So in the derivative, I calculate the derivative of the red curve. The derivative has a step. So the derivative here is positive, but then the derivative there is negative. So this would be here we are representing both spaces at the same time. Okay, so the derivative is not continuous. But now, if I'm more free, I can fit more polynomials. What happens is that now the derivatives are also continuous. And the higher the degree of this polynomial, so the more information you take around, the more derivatives will be continuous. I don't remember the specific details. I think with B cubic, there is continuity up to the second derivative. So the first and second derivatives are continuous, and the third derivative is not. So I have a better approximation to the green curve, that is the line, that is the signal that is underneath. So there is a signal underneath. This is the green one. This x of t. My black points are simply samples of that green curve. And then, because I'm interpolating the black points, I want to construct good approximators of the green one, not good approximators of my black samples. I want to construct good approximators of the green one and take samples from there. So the segments are bilinear, and then if I take, instead of now 4 samples in one direction, I take 4 samples in one direction, 4 samples in the other direction. So now I can fit a cubic polynomial in rows, and a cubic polynomial in columns. And it is not only that the first derivative, the function is continuous, but the first derivative is also continuous. And this is what is explained here, but we will not get it, and we will not enter into those details. Let me make some other reasoning why we need more points to estimate the derivatives. Okay, so we already know this. So we did this when discussing about the edges. So let's say I have a signal like this. No, I always do the examples in one dimension because they are easier to draw, but the same concepts apply to any other kind of dimension, to any other dimension. Okay, so we have the green curve, that is the one that is underneath. And I want to estimate what is x prime here. And we already discussed that we could approximate this by something like this. Okay, do you remember this? So we already said, okay, so this derivative should be approximately that. And should be approximately that. Should also be something like this. So I add one, sorry. Should also be that, right? And this is the left. This is the left first difference. This is the right first difference. This is called left because I'm taking the sample from the left. This is right because I'm taking the sample from the right. And probably you may remember that we had a different estimate that was this one. You remember that one? So we had this one too. So this is you to evaluate the derivative of the point, you need the point at the left, the point at the right. So, and it makes sense. So if I want to evaluate what is the slope of this green curve here at this location, this location, then if I take the information from both sides of that location, I have this information. And this is, so this one is taking the information from here, from there. What about this other pixel? This other pixel takes information from here, from there. And if you count, we have 4 pixels. So to estimate the derivative at these 2 points, you need 2 extra points, one on the right, one on the left. So in this square, we were, in the bilinear interpolation, we were focusing on this square. And we were focusing on the continuity on this square. But now, if we also care about the continuity of the first derivative, we need a point from the left and a point from the right. And the same top and bottom. Okay, so we will not get into the details of how this, this is what I have told you. So if I want to estimate the derivative in rows with respect to the rows, I need one sample from the left, one sample from the rows. It is one sample from the top, one sample from the bottom. If you want to do it in columns, you need one sample from the left, one from the right, and if you want to estimate this derivative in this direction, in the diagonal direction, you need these 2 derivatives, these 2 points. So we will not get on how the bilinear interpolation is constructed, but at the end, it has some cubic functions involved, cubic polynomials involved, and we can see the results. Okay, so we will not get into the mathematical details, but the procedure is the same. So the procedure is always the same. So you want to go from an original image to a small one, let's say. So you start at R prime, C prime, then you find a way to translate that coordinate into fractional one. Even let's do it with different color. So we have a fractional one. And then you have to interpolate. Then we have. So here in the interpolation is where we have these different schemes. Cubic, bilinear, nearest neighbor. And here in this transformation, it is where we have the scaling factor. So here we have the scaling factor. So we multiply by the scaling factor. So this is the geometrical transformation. This is the interpolation scheme. So those are two different things. So this is purely geometric. This is geometry. This one is interpolation. So those are two different steps. Okay. So what we have been talking and focusing is mostly about this part. The geometrical transformation for the moment has been very simple. It is just a scaling factor. Okay, so here we have an image, nearest neighbor interpolation, bilinear, bicubic. And we can see this is original, this is nearest neighbor, and you can see it is pretty bad, especially here at the buildings. So you can see the windows of the buildings. They are really, really badly represented. What is this effect? Aliasing. This is aliasing. And why we have aliasing in the windows? Because?
Yeah, very small details.
Yeah. So there are small details. So small details means high frequency, and the aliasing is an effect that is visible at high frequency. So this is aliasing, and this is bilinear, this is bicubic. Yeah, actually, in the bilinear, we still have a little bit of aliasing here. Bicubic is a bit better. And this is the opposite. So now we are zooming out, and this is with nearest neighbors. This is with bilinear. This is with bicubic. Any question? So the most important part of today is the interpolation scheme. And the interpolation scheme is nearest neighbor is we have been talking about polynomial degrees. So nearest neighbor is associated to a polynomial of degree 0. Bilinear to the polynomial of degree 1. Bicubic to a polynomial of degree 3. And the higher the degree of the polynomial, the better I will approximate the continuous function that is underneath. So this is the main basis from today. ¿No hay preguntas más?